Hello, good morning. So today I'm actually gonna go back to some of the more implementation issues and use this chance to maybe even ask some questions and do some demos. We were talking about 8051 for a while, and so we're gonna look at some more assembly code because understanding assembly is crucial to understanding how threads work. And one of our major projects is really to do threads package. And we're doing not only cooperative threads, but also preemptive threads. And you saw earlier with this example of interrupt version of UR to LED. Understanding how interrupts work is crucial to preemptive scheduling because that is the only way hardware can get control back from user program. Otherwise, user program just keeps running, right? So any interrupt can steal control back because whatever the user program is doing, it doesn't even know an interrupt comes in. The interrupt just happens, right? You set it up and then once in a while, interrupt comes and the user program doesn't even know it gets interrupted. Why? Because the hardware is safe state. In fact, ISR has to save some state too. And then after it finishes certain things, it restores the state, comes back, and the user program is exactly the way it's left out. It doesn't even know, other than perhaps the time has elapsed. Or maybe some what's called volatile variables may have changed. So that's the important concept. Some of you may still have trouble with the concept of interrupt because it's not exactly natural, but really you gotta understand how interrupts work. So these are examples to help you understand interrupt, right? So how this one works is you set up a serial interrupt as opposed to polling, right? And then what it does is it's not, I mean, it does the same check as what a polling does. So this one is, you remember this one, you type on the UART, send a character, and then have it print out that digit on the LED, right? So it does have to check whether it's TX or RX because they share the same routine. So that's why in this case, it checks if TI, that's the interrupt flag or the ready flag for transmit. But we're not really using transmit in this particular example. We're just receiving. So still, if it's TI, we want to clear it. Otherwise, it keeps interrupting us, right? And then RI, that's receive interrupt, so to speak. I mean, even though if you don't set up interrupt polling, it still pull the same flag, right? So by checking to see if it's equal to 1, if it's 1, that means there's a valid byte to be read in SBUF, right? So yes, you do that check, but in the ISR, you don't do a for loop or while loop or whatever loop inside the ISR because that's defeating the purpose of doing interrupt in the first place, right? So don't take your polling loop and stick it in the ISR. No, that doesn't make any sense. The ISR is there because hardware does that checking for you, essentially the polling. And then if it sees the bit change, it doesn't clear the bit, at least not UART, and then jumps to this interrupt service routine for you, okay? So that's what that routine looks like. You could write this in C if you really want to, but of course you have to make sure you don't accidentally link in these other functions that SDCC assumes that exist for clearing up your RAM bits. So here, if you want to declare a serial ISR, you do this and double underscore interrupt and then the number in the parentheses. So here it's if, right? It's not while. And then, well, this is not exactly equivalent, but this is really just a template for it, right? So if TI is is set, that means transmit ready, we really don't need to do much other than clearing it, right? And then the receive part would just follow this TI part. So if receive, so it's just linear code down. Don't do a while loop. Okay, so this I think we went over this. Just a quick recap since it's been a while. Now here, so if TI gets 0, if RI then that means there's valid byte to be read. So sbuff, you read it, put it in Rx data. Presumably this is a global variable. And then Ri clear it, and then display LED gets whatever value you read minus 48. Okay. Now you can say, okay, let me just stick a sbuff in here instead of Rx data minus 48. Is that going to work? Most likely, you can just try it because that's just a move out of it. And what the compiler most likely does is it has to compute the sbuff and then minus 48. So it has to move it probably into an accumulator and then do an add of minus 48, right? And then back in the accumulator and then do the LED display, right? So now the difference with this interrupt 4, as you remember, is that because an interrupt returns differently from a regular function. Regular function will use RET to return. An interrupt service routine uses RETI. And so have it generate the code, take a look to see if it really uses RETI. Okay. And then here, well, we could technically call a different function here. I'll call LED display LED. We've seen that before. But is that a good idea? Well, again, it's up to your judgment, and you need to know what the consequences of calling the display LED from here. Because there is a difference between what's called a function call versus a subroutine call. When we do an lcall instruction in 8051 or in most languages, it's what's called a subroutine call because that is an ISA supported concept. When you do it in a high-level language like C, and you just do the name LED, whatever, display LED paren, that's a function call. Well, a function call is a fancy version of subroutine call. So yes, for the control transfer and return, it uses the native instructions. But a function call does a lot more. What? Well, passing parameters, setting up your local variables, return values, right? The function is actually a higher level concept than the subroutine. And those things are not free. Those things take up resources as well. So you got to know what kind of resources and do you want to pay that price inside your service routine, okay? So one of the first things it has to do is what's called saving registers and restoring. That's all all implementations of functions have to save and restore registers. Why? Because, I mean, if you ever taken a compiler course or if you ever taken a look at generated compiler code, you know how compilers work. It's that you have some expression you want to evaluate, and you take like a plus b minus c and all those things. And then it's, but those things have to be broken down into simpler instructions because it knows how to do add, subtract, multiply, divide, and also shift maybe. And those have to be mapped to some, right? So your a plus b minus c, those have to be broken down into machine instructions. And that means it needs to use some temporary variables, such as R0, R1, R2 through R7, accumulator, maybe sometimes even the B register, sometimes DPTR, right? We've tried to craft some code like that. So those hold temporary values, right? And when you make a function call to you, it's okay, I'm making a function call. Well, what happens a lot is it transfers control to a separate routine. And presumably that routine is called from different places, right? And that means it better present that illusion that by the time it returns to whoever calling you, those other registers, if it ever has to use those same registers, will be saved and restored, just like an interrupt would have to save and restore those registers, right? So that the caller can continue using whichever register they use to store their temporary values, to store their local variables. So that might seem like, okay, what's the big deal? Well, it could be a big deal. Then we can take a look at some generated code to find out. And this is especially a big deal inside an ISR. Why? Because ISR just already saved a bunch of registers to present that illusion to the interrupted program. Okay, I'm going to save and restore so that you don't even know any registers got trashed in the meantime, because it does need to use some of those. Now, if that ISR calls some other function, guess what? Either that ISR or that called function has to save more registers again. It's like, hey, I just saved register. Why do I have to save again? Right? So you end up spending a lot of time saving, restoring these registers. And that's why, for a long time, especially embedded system programmers don't trust compilers, because they think compilers do a stupid job saving, restoring, spending all the cost saving and restoring registers just to something really simple, right? And it's not until the past decade or two they got a lot better. So then, okay, fine, start using compilers more. Otherwise, a lot of code for embedded used to be done all in assembly, just because it's quite a bit of cost. But that you still need to know that, because still, if you write this in the compiler, it may or may not be smart enough, because ISR usually is used in something timing critical. You don't want to spend a lot of time in ISR, and you want to be very frugal in your ISR. So still, ISR code could still be handcrafted, even for general purpose systems. Anyway, so let's take a look at the generated code. Okay, that interrupt led.lst, or you can look at ASM. So it shows. I mean, yours might be a little different, but this is what mine looks like. So what does it do? It pushes bits, pushes ACC, pushes B, pushes DPL, DPH, pushes what's 0 plus 7. That's the absolute address for register 7. Because R0 through R7 get mapped to direct address 0 to 7. So 7, 6, 5, 4, 3, 2, 1, and push PSW. And that's just on entry to the ISR, okay? It pushes those registers. I said, I didn't write this code. Well, the fact that you use a high-level language construct in the form of a function means compiler does this work just so that it can implement the function abstraction, okay? This is the cost. So a compiler, just to be on safe side, yes, would have to push and pop those same registers so that it can safely use those registers, okay? So, and then you keep going. Well, okay, now we're getting into the body of the code, because your listing will show also what your C code looks like. So it does the move of constant or immediate 0 into PSW if Ti equals not, well, if it's true, right, it means not 0, that means the bit is set, then do this. So JBC, Ti gets 0, and then, so that means jump is bit is clear. In other words, in C, you think if true, I do this. In assembly, you think if it's false, I jump out of it, right? So that's JBC. So jump to this 00113 $, that's a label. That's a local label, okay? So what's that? So that's this label here. So that skips the part for the. So I actually took out some stuff. Anyway, then there is if Ri, then jump if not bit, right? So, oh sorry, no, JBC means jump and clear bit, right? So if the Ti is set, then it clears Ti and then does a jump. So that was what that was supposed to be. Yeah. And JMB is jump is not bit, okay? So if Ri, then not bit. If Ri is false, then skip out of this, right? So it jumps to label, which is at the end. Now it does a sbuff read. So as you can see, it's moved from sbuff into Rx data. That's another direct address. And then Ri is cleared, so it's clear Ri. And then display, that's to call that function. Well, what do? Well, you load the old value into A, or the current value or Rx data into A, and then does the add of what's hex D0? Well, hex D0 is really just minus 48, right? Remember 2's complement representation? You should all be very comfortable with this. I shouldn't need to review this, right? So that's you basically flip all the bits and then add a 1. That's how you get the negative version of it in 2's complement representation. Then move so the result, move to DPL. Why DPL? Because in SDCC, you pass parameters. If it's a single byte, you pass in DPL. If it's 2 single byte parameters, pass in DPL and DPH. Or if it's a 2 byte parameter, passes in DPTR, which is concatenation between DPL and DPH. And that's so that it can make the call to display LED, okay? And then after that, returns back, pops PSW, pops registers 0, 1, 2, 3, 4, 5, 6, 7, pops DPH, pops DPL, pops B, pops ACC, pops bits, before it does the RETI. It's like, what? Spend way more code just on pushing and popping all these registers compared to the little code for me, right? And then that doesn't even count the display LED code, right? And then, so that seems like not such a good idea, does it? Right? So, so of course, no. That could also mean SDCC is not doing a great job. But that's in general, that's kind of what you have to assume. You can't assume your compiler to be that smart compared to when you craft the code. So if you have to craft the code by hand, then you then can decide which ones actually get affected and which ones don't need to be saved and restored. Okay. Well, so, okay, this is outside the scope of this course. You can take a compiler course to learn about this. There's convention of what's called caller save versus callee save. So caller save, they basically saves all of those that it uses once preserved. And callee save means it saves those that it will use. So, and then when, so it's an agreement you have to make between the caller and callee. And so that is a convention that has to be consistent. So there's no one or the other way to do it, and then there's of course trade-offs there. Sometimes, I mean, in one way or the other, you always may have additional registers that don't need saving, but you save anyway and restoring them. So compilers, unless you inline everything, but then that increases code size. So there's no just one way to do things. Okay, so so that is for week 3, and then I'm gonna quickly bring up week 4 on. So we did go over. This is not the one. Oh yeah. Oh, okay. Well, actually,